Hi everyone, welcome to the first of a series of 6 videos clips which I'll be actually teaching you a topic called functions. In this first segment, I'll be introducing the idea of functions and I'll give you some examples of functions. Now please download the handout on 5.1 under the Introduction to Functions. Okay, what is actually a function? From the handouts that you have, it says that a function is a rule or relation which assigns to each and every element x in x one and only one element of y in y. Now what does that mean? Just imagine that we have this set of elements which we call it capital X. This will be a set that represents some numbers in this set. Okay? And then we have another set y over here. A function is basically a rule or relation which assigns to each and every element in this set to one and only one element in y. So that means that this element cannot go to two other elements in y. It can only go to one. However, a function allows another element here to map to the same y. Okay? But however, it doesn't allow this element to map to two values of y at the same time. So that means this element can map over to here, and this element can map over to here, and this element can actually map over to here. Okay? This is what the diagram looks like for a function. And the set of x values in this set of x is called the domain of the function. And all those y values that is mapped into the set y, we call it the range of the function. The domain of the function is denoted by d of f. This is what we call the domain of the function. And the range of the function is denoted by r of f. Okay? And remember, in any function that you define, there are two important things to take note of. That is that you must indicate what is the relation that maps this to that. At the same time, you must tell them what is the domain of the function. Okay? Now remember, the domain of the function must always be stated and the rule must always be stated. To find the range of the function, you always use the graphical method to actually sketch the whole graph of the function and then look at the y values. Okay? And the set of all the y values will represent the range of the function. Let's take a look at the first example in the handout. It says that a function f is defined by this rule. F, okay, colon, x maps to 3x minus 1 over x plus 2. Okay? X is greater than 2. Now that is how we will write a function. This part is called the rule of the function. Okay? And this part is what we call the domain of the function. Okay? So that means that, for example, if I want to map a value, say 1, okay, it will be mapped into 3 times 1 minus 1 over 1 plus 2. That gives me 3 minus 1, 2, 2 over 3. So this value here is one of the elements in the domain of f. And this one is one of the elements in the range of f. Let me give you another point. Suppose it maps 0, right? Sorry, I cannot say map to 0. So say I map it to 3, right? And this gives you 3 times 3 minus 1 over 3 plus 2. And that gives me 5 over 5, and that gives me 1. Although you can define those two values, this x equals to 1, unfortunately in this example, is not inside the domain because our domain is x greater than 2. Whereas this number 3 is inside the domain because it is under the set x greater than 2. Okay? So, but whatever the case, you can map a particular point to the other point. If this point belongs to the domain of the function, then this point will belong to the range of the function. right? However, if this point is not in the domain of a function, this one will not be in the range of the function. So then, having said that, right, that means that our key thing here is to be able to understand what is the range of a function. Okay. Now, based on my question, imagine that my question is x greater than -2 now. Okay. So what will then be the range of the function as being asked in the question? For that case, right, we will first sketch the graph of f. How would the graph of f looks like if you use a GC to sketch? Okay, there will be a vertical asymptote, x equal -2, right? And then there will be a horizontal asymptote here, which is y equals to 3. Okay, we'll talk a little bit more about the vertical asymptote as well as the horizontal asymptote in the next chapter under graphing techniques. Okay. In the meantime, we take it that we have these two values here, and the graph will look something like that. Okay. And this point that it cuts the x-intercept is x equal 1/3, and this value here is y equals to -12, like this. Over here, we should not be sketching anything because we are only interested in a function where x is greater than -2. Okay, x is greater than -2. So how are we able to find the range of the function? Remember I mentioned to you, the range of a function are all those y values, okay, based on the x values that is defined on it. Okay, so based on the x values from x between -2 onwards, the y values will start from -infinity all the way to 3, excluding 3. So we will write our range of the function as all those y values, they are real numbers such that y is going to be less than 3. Okay. Another way of writing the range of a function can be that we can write the range of a function as from -infinity to 3. But you exclude the -infinity because -infinity is not a real number. And you exclude 3 because 3 represents the horizontal asymptote. We are excluding that as well. Okay? Now, this way of writing the range of a function is what we call in set notation. Okay? Which is required, right, in this question. Otherwise, if the question never really insists that you write in set notation, you can leave your answer as an interval. Okay? That is example 1. Now, how do we check whether a particular relation or rule is actually a function? We use this thing called a vertical line test. Now, you turn to the next page of your handout, vertical line test. Now, in vertical line test, it says that a relation is a function if any vertical line cuts its curve at most one point. Now, let's revisit the last example. In this last example, you notice that every vertical line cuts at only one point. Okay, right? But it also can choose not to cut the curve at all. That's why the definition allows it by saying that it cuts any curve, the curve at most one point. That means you can cut at one point or you can choose not to cut. Okay? But it cannot cut at more than one point. So if I draw a graph that looks like this. Okay? Now this graph does not have the property that it cuts at most one point. Reason is because you can see that the vertical line here cuts at 2 points here. Okay? So this type of graph is only a relation, but it's not a function. Okay? Now let's look at the next section of our materials here. It says that we are interested in studying what is meant by a restriction of a function and what is the maximal domain. Now, it says that let's consider two functions. The first function is fx given by x cubed minus x. X is a real number. Now this is the rule of the function, and this is the domain of this function f. And then it also gives us another function that is gx equals to x squared plus x and x greater than 1. These two functions, right, are actually having the same, this one should be minus x, in the notes. Okay, so these two actually have the same rule, However, this domain is only a subset of this domain. So this is actually what we call a restricted function of this f. So we say that g is actually a restriction. Okay, restriction of the function f, okay, on this set 1 to infinity. Okay, restricted function from 1 to infinity. Okay, because it shares the same rule. However, the set of values where g is defined is only part of f. Okay, and then gx and fx will always be equal for all those values in the restricted domain of g. Okay, and this is what is meant by a restriction of g on f. I'll give another example that is not in your handout. Suppose my definition of fx is as follows. Okay, all right, and then my gx is defined as follows. Okay, though these two functions have the same rule, right? However, this is not a restriction of each other because x contains a value 1.5, which is not found in f, whereas f contains a value 5, which is not found in g. So f is not a restriction of g, neither is g a restriction of f, though they have the same rule. Okay. Now in the next example that we'll be sharing is on the maximal domain. Okay. Let me just erase the board a little. Okay, we go on to the example here. It says that find the maximal domain of this function. And its range. Now, what is actually a maximal domain? From the handout, it says that suppose a domain of a function is not stated. Okay, just like in this example. Okay, it is usually understood that the domain that is going to be defined is the largest possible domain, or we call it the maximal domain, for which the function is defined. So in this example, we are supposed to look for what is the biggest set, what is the largest set that is possible for which the function is defined. To do so, right, we can actually sketch the entire graph. Okay, if you sketch the entire graph using the graphing calculator, you will notice the graph for this function looks like this. Okay. And this value here is 0, this value here is 1/4. So that means that the graph is defined for all those values of x except this portion here. So that means that we can actually say that based on this graph, the function is actually only defined for x less than or equals to 0 or x greater or equal 1/4. Now, of course, this method of checking on the graph may be a little bit risky in the sense that you may not know what happens later on. You may want to zoom out and zoom out to have a feel whether is the graph really defined beyond it. A more mathematical approach is to ask ourselves, when is this function defined? It is defined when this expression inside the square root is greater or equal to 0. Because when this expression is greater than 0, you can take the positive square root. So that means that we can actually also say that the function f is defined when 4x squared minus x is greater than 0. Solving this inequality is an easy process. You just have to take out x, okay, form a quadratic equation, and you use number line method that you have seen in inequalities chapter. Submit a number more than 1/4, let's say 10 into the x value, you realize it's positive, negative, positive. So we are looking for greater than 0, that will mean x less than equal to 0 or x greater than equal to 1/4, which is the same answer as based on a graphical approach. But this method, of course, is more mathematical. It allows you to immediately know that what you are getting will be the correct answer, for sure. Now, based on that, you can actually look at the range. Unfortunately, range, the only way to do it is to sketch using a GC. When you sketch using a GC, be very careful. Always try to zoom out your graph a little to make sure that it doesn't stop somewhere, okay, and it's not defined. Okay, so based on this diagram, you can see that the range of the function, remember, are the y values. So it will be from 0 to infinity. So we can say that the range of this function are all those values from 0, inclusive, to infinity. The square bracket here represents a 0 is a value inside the interval. Alternatively, you can leave your answer in set notation, where all the y values such that y greater equals 0. Okay, that ends off with this example. Now, last part of my handout, I'll be actually running through what is meant by a one-to-one function. Clearly, from the name itself, it is actually a function to say. But a one-to-one function means that every x value goes to the one y value only, one and only y value. Okay, and we cannot allow another x value to go to the same y value. So that means that in the previous beginning of my lesson, I actually give you two sets here, x to y. And I say that this x value can go to this y value, right? And another x value can go to another y value. Okay? It cannot go to two y values at the same time, or else it will not be a function. In a one-to-one function, it also does not allow two y values to give rise to the same y value, two x values to give rise to the same y value. That means that this kind of relation or this kind of function is not allowed in a one-to-one function. How are we able to actually identify which function is one-to-one? We use this thing called a horizontal line test. What is horizontal line test? Now, horizontal line test, from the name, implies we are going to use a horizontal line to check. Okay, let's take a look at a previous example that you see. This is clearly a function because every vertical line cuts the graph at most one point. However, it is not a one-to-one function because every horizontal line cuts at 2 points. Okay, so this violates the definition of one-to-one function. Okay, you can create a lot of examples here. Okay, you can create an example like looking like this. This is a famous y equals to x squared graph. Okay, so you can see that the horizontal line cuts at two y values. So it is not a one-to-one function. Then what are some examples of one-to-one function then? An example of one-to-one function could be the famous y equals x cubed graph. For the y equals x cubed graph, you notice that every vertical line cuts at most 1 point, so it's a function. Every horizontal line cuts at 1 point also, and therefore it is a one-to-one function. Okay. In the next chapter, on the next video segment, we will actually be going through inverse function. Okay. So please go to our next video segment now and look at what is the inverse function. Thank you.